Good day to you from Anagalactic on the 17th day of June in 2026, a Wednesday here. Over here you see our famous mascot, whom you will find at large in the sky somewhere at all times, that old devil moon. I always like to put this up on the screen at the introduction to a video because it reminds us that the universe does contain a geometry and it does appear to be mostly curvature. We use linear geometry in order to do very constructive work on Earth, and that linear geometry has led in all directions for the human race on the basis of discoveries in technology which run apace with the discoveries made in mathematics, in physics, and of course in geometry, which is the coordinating function of geometry, is to coordinate the use of numbers with the reality of physical space. So Euclidean linear geometry has been remarkably successful. This video is devoted to an orientation which I find is useful just to interject what we're actually doing. What are we trying to accomplish? In this case, what am I trying to accomplish? On behalf of science, I do attempt to catch up with science and perhaps even contribute if that's reasonable from a non-academic point of view. I am a retired gentleman and I make these videos mostly to coordinate my thoughts, which do revolve around this geometry which has ultimately fascinated me, spherical geometry. So we're studying spherical geometry, and the good old moon is a very good example of that we are indeed dealing with reality when we're talking about spheres. And in fact, if you explore the concept of the sphere, just search your memory banks for examples of spheres. Probably the most familiar sphere is the moon, since you would tend to see that before you saw the Earth, since the Earth is underneath your feet, and you would have to extrapolate in order to deduce that the Earth is in fact spherical. Whereas by looking at the moon, you can tell right away there's something up in the sky that is spherical. What about at microscale? The proton is considered to be spherical. I don't believe that requires explanation in an overview, that the proton you probably could accept rather readily, that it is spherical. What about the electron? That too is spherical. What about the photon? Christian Huygens showed that the light product that goes through the universe, whether you consider it to be made of particles or it is simply a waveform, which may not be simple, but it's either a waveform or a particle, and I think you know that it can be one or the other, and it's kind of superpositional, it's kind of both at once. Even the pilot wave theory of de Broglie, which was expanded later by David Bohm himself, attempts to unite the concept of a spherical particle, a photon, with a wave which could be construed as a spherical function. Although a wave, as you know, is not a closed curve, whereas a sphere is a closed curve. That term closed is rather remarkably profound when you consider that the family of lines, which then extends to volume space, the family of surfaces, has a range of eccentricity, which is what we covered in the past couple of videos. The eccentricity factor, which is another metric that is very similar to the metric for curvature, which Friedrich Gauss explored quite extensively. So we have a very simple metric for the straight line, which is simply a I'm looking for the word. It's a very simple form of curve that has no curvature, but it is a line. If you take the line, and I'm just going to do this visually, and we'll have some diagrams in a moment, but if you've tuned in for the past couple of videos, you know what diagram. In fact, let's bring it up now. Here is what I consider to be one of the very best diagrams. This is from Wikipedia. If you need a link to find that article, I don't think you'd have any trouble finding it, but this is the family of curves. Why is it called a family? It's because there is a range of, for instance, probably the simplest answer is concentrating on that red figure, which is the only closed line in the family of lines. It has closure because it's called the family of ellipses. And I think you can already guess why it's called a family, because an ellipse has a variable eccentricity. What is the actual range? Well, that E value is what attempts to, well, actually successfully attempts to metricize curvature on a concept called eccentricity. Now, expanding this, I just wanted you to see that the ellipse has the value here of 1 proportion 2, which is the correct way to read that fraction. 1 proportion 2 is its eccentricity. And to give you an idea of what is meant by eccentricity, just expand this one more time. Look at the black line, the straight line at the extreme bottom. That has an eccentricity of infinity. So this is a range from the fractions less than 1 all the way to infinity. It does not show closure in the metrical range to the inner. But if you were to look at this diagram in Wikipedia, you may be able to see that there are a lot of gray lines that are basically the transformation range between these curves. Now, I hope that it doesn't sound baffling. The work done by Johannes Kepler and by Sir Isaac Newton and by Father Roger Boschkovich all concentrated. They concentrated very much at a certain phase of their work on the family of curves, and from this we have a very useful range of curves, which at one limit, which here is the eccentricity of infinity for a peculiar line, which is called the straight line. It's one of the lines in the family of curves. It has 0 curvature, but it has infinite eccentricity. So what we want to discuss here is what is meant by eccentricity. When you go upwards, there is actually a reflection around that straight line. And the hyperbola, as you undoubtedly know, actually executes 2 curves around what is called a directrix, which would be a straight line, that makes the family of hyperbole a family of reflected curves. The other curves do not reflect around a directrix, in this case the black line. So looking up is what these scientists did. That is Kepler, Newton, and Boschkovich, just to name probably the 3 most famous names. In their work with the family of curves, I want to make this very simple because this is the purpose of a scientific presentation. I should say one of the essential purposes of science is to simplify, because understanding is what we want. It's not enough to describe, and it's not enough to describe and then prove, although you need to do both. What is desired is understanding, which is quite an interesting concept. We're trying to understand what the universe is saying. I like to put it that way. I believe that's a reasonable way of putting it. We're learning from the universe, both on Earth and by looking up into the apparently infinite expansive space. And we're heading towards infinity now. I'm greatly attracted to the concept of infinity, not just because it's problematical in many situations, but because it's something we need to understand. And I think it's quite a challenge to understand what is meant by infinity, because a term like that will have context. There is a perception of the infinity of time. Bidirectional, in fact. If you go back in time, can you reach closure? If you go forward in time, does it open up forever? So when we say forever, that's a temporal concept of infinity. The spatial concept of infinity is what I would say is a major topic in astrophysics, but really it's something humans have always been interested in. And in many of my early videos, I spoke about my own personal experience, which I believe is shared by virtually all children, that at some phase growing up, trying to reach maturity, but you're still a child, you end up looking at the night sky and wondering, how far can you see? Well, that appears to be a common goal of humanity, at least in the sense of using telescopes is just fascinating, because you can see further into the sky. And now we have space telescopes who can see, which can see, not who can see, but it's we that are looking, but the telescopes, such as the James Webb, and of course the famous Hubble telescope, its predecessor, there's whole families of telescopes now that probe various ranges of the electromagnetic spectrum, which is not just visible light. In fact, the James Webb telescope is kind of offset. Using modern technology, quite remarkable, we are able to see ranges of light which are not visible to the human eye. In the case of the James Webb telescope, we want to head towards the red end of the spectrum, which is infrared, is the first wave band region, which we cannot see, but we can feel it. So it's still energy, but it's not visible to the eye. And that's important because the red-shifted light is shifted towards the red. I think you know how redshift works, but it's quite simple, really. The further away a macroscale object is, in this case, galaxies, but there are quasars, but galaxies is the main topic of investigation. I should say that that's the one that I'm most interested. Well, quasars are an interesting topic, which we can't go into now, because that would be a little off topic. But in terms of sphericity, the universe itself, from our perspective, appears to be spherical. It certainly isn't cubic. In other words, everything is curved. And the edge of space, as far as we can conceptualize it with our visual perceptual system, which extends in the human mind into the imagination, such that we can at least conceive of infinity in some way, it does appear to be a spherical infinity that we inhabit. Where it is commonly said, and I believe you've heard the same thing, that any place you are in the universe, such as on Earth, is a virtual center, but anywhere else you are in the universe is also a virtual center. Because of I'll just use the term homogeneity, there are technical terms for the uniformity of what's in space. That no matter which direction you look, you basically can't tell the difference in direction. So it does not look to us as though the universe has a center, as if it were a sphere, except this rather paradoxical situation that anywhere you are is the center, which does not really make sense. So this is why infinity just comes up in the most interesting circumstances, contexts, all the way from being a child and just asking in awe and wonder, how far can we see? Science does not yet have an answer for that, although there are some models. Sir Roger Penrose's cyclic model is most fascinating, but no solution to the cosmological equation or geometricization, no model can avoid a paradox. And it's just a mental exercise to try to model the universe. Well, of course, right now, the cosmological expansion model is in the lead. There really is no serious contender with the cosmological expansion model. which used to have the name Big Bang, a rather silly name, but cosmological expansion is just a restatement of the paradox. Because ultimately it doesn't make physical sense to say that the universe is expanding. It's an extrapolation on a measurement, though. Really, it's an extrapolation on the measurement of redshift, which is a linear relationship between distance and the redshifted light. So, coming back to our diagram here, it's most interesting to see that infinity occurs both in the metric of curvature, which Gauss was really the man who is accredited with that metric. That a circle, you could say, has a certain curvature and try to assign a number to it. Well, then you need to compare it with some other curvature and give that curvature another number, and then you come up with a mathematical formula for curvature. If you try to do that, and you say that the circle has x value of curvature, and then you extend it into the family of ellipses, which would have to be on one of the two axes. So this would be, I believe it's called oblateness, whereas the vertical stretching, which is simply orthogonal with this form of stretching. Really, you could say it could be stretched in any circular direction. So it turns into a family of curves, is the net result of that observation. Well, that's what you see in this diagram. And beginning with the red ellipse, its value of 1 over 2 is that particular ellipse. And that's where the family concept comes in, because you can see that that is stretched vertically from ultimately a circle would be the most compact in the family of ellipses, because the vertical aspect and the horizontal aspect are equal. And that could be considered in several senses. It's essentially unity. So you could say that the circle has a curvature value of 1. But it does depend on what you're attempting to measure. Why would the circle be 1 in comparison with what? And in this system of eccentricity, that is not what's being measured. It's not curvature, but of course it's related to curvature. So what is this eccentricity? Well, normally you would look for 0, 1, and perhaps infinity if that's in the system, just to test it to see what those values are. In this system of eccentricity, the green line, which is the parabola, has eccentricity of 1. Now, what is meant by that? In order to answer that, by observing this geometric diagram, we want to answer that geometrically, even though we're using numbers. Because, of course, the metric correlates numbers with something in the geometric system. This system is the family of curves, as it is so called, and it is so called, first of all, because the ellipse is not just one thing, but the parabola is. There's not a family of parabolae. This has nothing to do with rotating it in any direction. This is simply examining one aspect of the family of curves plotted on a plane, which in this case is opening up. Again, the ellipses do not reflect around the straight line. Only the hyperbolae do that. And you can see a little piece of the hyperbola that's the same as e equals 2, which is another family of curves similar to the ellipses in the sense that that value of 2 applies to that specific hyperbola. So what's the range of the hyperbolae and what's the range of the ellipses in this metric system for the measure of ellipticity of these curves? Well, the value of 0 is not shown, but you can, we'll get to 0, and the value of infinity is shown as a zero curvature line. So 0 and infinity are certainly related in this metric. So that's partial. We have a partial answer because the lower bound is 0. We would assume, we actually can't see that, but you can see that the ellipse collapses down to what we would assume would end up being a circle. But does it collapse to 0? It's important when giving a range of values whether the bounding values are part of the range or if they're the limit which you cannot reach. And we see both of them here. Well, let's explore that and make sure we know what we're talking about. We do see infinity, which there is nothing beyond that. And we can see by implication that there's a 0 in there, which would be the limit, either inclusive or non-inclusive. But now we want to find the value of 1 in the system because unity is a magic quantity. And there are reasons for that that can be stated quite logically, but it actually gets quite deep. That the number 1 has an extraordinary significance, both in mathematics and in geometry. Here you see that the eccentricity of 1 applies to a unique curve called the parabola. In this diagram, there are no parabolae. If you continue to curve upwards so that you're going into the family of ellipses, there's no in between. The parabola is a boundary. It's a boundary between the family of ellipses and what's below that blue line, the family of hyperbole. It's the transition curve. Now, you can see that there are 4 curves shown here. And reading up from the black line to the blue to the green to the red, I want to characterize each one of those curves. The black line has 0 curvature, but in this metric, its eccentricity is infinite. So essentially, if you go through the ellipses, past the parabola, through the hyperbole, you're going in increasing eccentricity. Where finally, the terminator is E equals infinity, and that's inclusive in the system. So infinity is in the system, is 0. You would assume so, but we can't actually see it. 0 could be considered that point F, but that would need to be proved. And that's exactly what we want to do right now, is to be quite precise in what is being measured here, a valid measure of curvature using the metric of eccentricity of the curve, where the 0 curvature line is unique. So reading up, we have that. It's not a family, it's the straight line. And then in between the black line and the green line, which is the parabola, let's jump right to the parabola. That also is unique. There's not a family of parabolae, and there's not a family of straight lines. There's only one straight line in the system, and it has the value of infinity. So it's a boundary. And in the system, you have the parabola, of which there is not a family. It is also a boundary. So of the 4 lines shown here, 2 of them have that characteristic of being unique, not part of a family, but actually forming a boundary. But the other 2 lines, the blue one is representative of a whole region that's between the green line and the black line. That's where the that's where the hyperbole are. And it's continuous, but it does have a metric in this system. So the concept of continuity, we will be encountering that, but without going into that concept at this time, all of the parabolae have a numeric value between 1 and infinity, but not 1 nor infinity. And those constitute the whole numbers. That could be argued because of the concept of continuity through the whole numbers, numbers between 2 and 3, for instance. How many numbers are between 2 and 3? Well, there are no whole numbers between 2 and 3. So it's just a little bit inaccurate to say that that's the range of the whole numbers. What is the right way to say that? It's the range of numbers between 1 and infinity. In other words, no numbers less than 1. In fact, 1 is not included, nor is it included in the family of ellipses. So now we can proceed through this going from bottom to top, that the straight line is a boundary that has the eccentricity infinity. The family of hyperbolae are in between the straight line and the parabola, such that it is in the range of all numbers greater than 1. So the family of hyperbolae, being measured by the eccentricity value of the hyperbolae family, is in the range of greater than 1. And that's all you need to say. It's implied that it goes to infinity, but that is actually explicit. Infinity is not included, because that's a unique line that is not part of the family of hyperbolae. It's necessary to go... I know I'm saying this kind of over and over, but this is so important because of what comes next. All the numbers greater than 1 form the eccentricity value for the family of hyperbolae. Well, what about less than 1? That's the range of the closed lines. There's only one closed line here. It's the ellipse. That has closure. It doesn't go to 2 infinities. The straight line goes to 2 infinities. They actually have an additive relationship. That's quite profound because now we're talking about the operators for numbers. Add, of course, is the simplest of the operators. Well, if you have plus infinity and minus infinity on the infinite line, now you can say why it's infinite in 2 directions. It's because its eccentricity is infinite. So now you have 2 infinities that are related. How are they related? They add to 0. So there's an interesting relationship between infinity and 0 in this system. So there's just a little insight. We're going to come back to 0 in just a moment. In fact, we're heading towards 0. So you begin at infinity that's non-inclusive in the hyperbolic family. The family of hyperbolae is represented by all the numbers greater than 1. And that's actually a very good definition of numbers. But what about numbers less than 1? Okay, now we're at the green line where the eccentricity is 1. When you keep going upward past the parabola, you enter the realm of numbers that are less than 1, which in the way we compose numbers has to be written as a fraction, which is why this particular ellipse in red has the value of 1 proportion 2. That is the correct way to say a fraction. I said in the prior video that that should not be read as division. Rather, it should be read geometrically. It is division if you want to say it that way, but conceptually, you're not dividing anything. It's the proportion of 2 quantities. And that's what we want to explore here. When you're in the range of the hyperbolae, that's all the numbers greater than 1, all the way to infinity non-inclusive. If you widen that, it would become eccentricity 4, 8, 16, to say it geometrically, all the numbers in between the whole numbers, which is generally called the set of real numbers. But it's the set of real numbers greater than 1, which is quite interesting because if you continue on this continuous progression from infinity, which is a boundary number, to the parabola, which has the value of, shouldn't that be 1 over 1? You could easily write it as 1 over 1. You must write it that way. Do you know why? It's because it's a curve. And if it's a curve, it has to have a two-component value, a proportion. That's what this shows. And I think that's one of the most profound insights that I personally have ever had into the nature of mathematical geometry or geometric mathematics. The relationship between lines and numbers is much more accurately shown here than Euclid ever imagined. And this is why it attracted Johannes Kepler, who was able to deduce by looking at this. He actually composed this sequence. So did Newton. And both of those men were working on gravity. And then along came Roger Bošković right after Newton died. Of course, Kepler lived quite a while before Newton. But the lives of Newton and Bošković overlapped. And Bošković drew this same thing as well as the other two men. But he was not talking about gravity. He wasn't thinking about gravity. He was thinking about the interaction of fundamental particles. And I think that's another profound insight, which came my way just 2 years ago. So this is all rather new to me. I think it's new to everybody. And what I discovered, I want to begin to broach to you now in terms of number space. Because this is not just the family of lines, which are curved lines. This is the family of curves, of which the straight line is a peculiar example. Quite similar to the parabola in the sense that there are 4 lines, 2 of which are unique and 2 of which form families. That's kind of magical that all lines can be classified as one of 4 kinds, 2 of which are boundary conditions. So really, if we disregard the boundary conditions of the straight line and the parabola, this shows the continuous family of curves. But if you exclude the straight line from the family of curves, you also should exclude the parabola. But you can't, because both systems are continuous, which proves that not only is the number 1 in the system, but to the proportion that 1 is in the system, so is infinity. And that's proved by this diagram. So infinity can be conceptualized as a number, which is quite a remarkable statement, because what is it quantifying? In this case, it's quantifying an abstract concept called eccentricity. So eccentricity in this diagram goes to infinity, where now infinity actually has a geometric meaning. And so I want to expand on that perception, because this leads to a discovery in our conception of numbers. Infinity now becomes a number in a number system, but can infinity be a linear number? We already discussed that if you consider the straight line to go to 2 infinities, they add to 0. And that's the use of the operator add. You could say that. This led to a new theorem, which I'm now going to explain to you. But I've never used this diagram to explain it in the many times over the past 4 years that I've given you the proof for a new number system. You can see the new number system here. What's the old number system? It's the system of 1-component numbers. All the numbers in between 1 and 2, for instance, are single-component numbers. And now I want to show you something which you can see on this diagram. I want to describe it and then explain it, and then let you make the decision, what did I just say? I want to do it this way so you discover this for yourself. That's the essence of understanding. That's the aha moment. And I want you to gain that, because I think it's one of the most thrilling things about science, is you're trying to understand something, but you're not sure that there's anything there to be understood, because you can't prove it to yourself. But once you see that you can prove it to yourself, It's something akin to, I don't want to say orgasm, but that actually was the word that comes to mind. It's kind of a mental orgasm. So, sorry, but I'm searching for analogies here. So let me show you what you see, and then I'm going to describe what you see, and then I'm going to explain what you're seeing. Look at those four numbers. Just to make this a little better, there. So starting at the bottom, we have a one component number apparently. It's lazy 8. And now you can see that that is a number. Is that a linear number?
Don't answer that, I'm just throwing that out.
Now you see this particular hyperbola has eccentricity 2, which is less than infinity. although we'll come back to that as well. And if you go up, you're going down from infinity towards 2. So everything between this black line and the blue line consists of all the numbers that are in between infinity and 2. If you go past this particular hyperbola, you're still in the range of hyperbole, but now these are all the hyperbole in between value 2 and 1. But once you get to the value 1, it's no longer a hyperbola. It turns into a parabola. Sorry, I've been thinking about this for 4 years and it never ceases to amaze me. I hope this amazes you too. I haven't shown you yet, but you may be starting to guess what we're coming to is a new number system. Hold on. So now you get to the parabola, which has the unique value 1, and there's nothing like the old parabola, boy. It has eccentricity 1, and that's it. That's what you get. So now you keep going, and in between the green line and the red line, you have a family of ellipses whose eccentricity is less than 1, but greater than, and how do you read that funny number that doesn't look like the other numbers? Isn't that 2 numbers? Yes, it is. Let me just suggest something to you. The reason why the ellipse has a fractional value consisting of 2 linear numbers is because it's on a plane. And really the other numbers are not drawn, they're not written right. Because you've decomposed a 2-component number such that e equals 1. Well, where's the other part of that number? Shouldn't it be a fraction? Yes, it should be a fraction. Well, why is it not written as a fraction in Wikipedia? Well, I think you know from school what you were told. Oh, it's obvious, Scott. What are you, stupid? Sorry, but you can write 1 as 1 over 1. Are they the same number? I was told that they are. It can be proved numerically that they are the same. But what's the difference? Well, really the difference is that you don't have to write 1 as 1 over 1. But if you have a number less than 1, you're going to have to write 2 numbers, darling. There's no way around it. So, are numbers less than 1 some peculiar form of number? Not necessarily. It just looks that way because you've chosen not to write 1 in 2-component form. But shouldn't you? I would say, to make it notationally consistent anyway, that parabola should have a 2-component value. Well, it does, because for the same reason you can write 1 over 1 as just 1. You can write 1 as 1 over 1. Do they mean the same thing? I leave that to you to answer, but we're going to go forward. I will show you that you actually had better write that as 1 proportion 1, which is 1 over 1. And this number 2 is in reduced form, which you cannot do on the plane. So Wikipedia may have made a hideous error. Now, I'm not saying that. I'm saying from one point of view, it's really bizarre that since these are planar, a curve always occurs on a plane. And so a plane we already know has an x and y value. Well, that's what that 1 over 2 is. Essentially, it's one of the two numbers that you have to have for anything on the plane. It has to have a 2-component value. Because you're not on a line. Only a line has 1-component numbers. Then why is this eccentricity written as a 1-component number when that's ridiculous? Because it's a planar value. Well, then it's 2 linear numbers. And so this should be written as 2 over 1. Making this hyperbola the reciprocal eccentric value of this ellipse. That's simply a mathematical statement. So let's go through this again. Here's infinity, but that line is being drawn on a plane. So that should be infinity over 1. It must be. I say so. I've proved this, and we're getting to my proof. This is extraordinarily a productive sequence, as you're about to find out. I call this the bootstrap theorem. It leads into the bootstrap theorem, which is a proof of something I want to prove. But I haven't told you what it is yet. So this is a unique approach that I haven't thus far used. So this is another approach to what I discovered, which is a new number system, which sounds a little megalomaniac. But you can see that there are 2 number systems depicted here. One is a 1-component number system, which works for anything over the value of 1, inclusive of 1. But anything less than 1, you can no longer write it as a 1-component number. It's always a fraction. So why not just write them all as fractions? Because any number over 1 can be reduced to the numerator. Am I right? I believe that's what we were taught in school. Numerically, that's true. But this is geometry. And so we want the numbers to conform to the geometry. And quite frankly, they don't. Because 3 of the numbers are written incorrectly. Because we're not talking about a straight line. The straight line is now simply a special case of the family of curves. So let's rewrite these and do this in your mind. E equals 1 over 2. That's correctly written. It's a fraction. Well, this E should be 1 over 1, and this E is 2 over 1. And most significantly, this number here is infinity over 1. Our sprinkler system is coming on outside, and the door is open because it's going to be another 100-degree day. So you may hear some sprinklers in the background. I did mute this for when the train went through. It's remarkable, even in the middle of the night. It's not even dawn yet here, but the sprinklers are coming on because they do it automatically in the train. Oh, God. Anyway, I have to be aware of what you may hear in the background. So, so we've come 47 minutes to get to this new number system. Is it new? Well, if I want to sound megalomaniac, yeah, I discovered this new number system. No, not really. Yes, I did, but I haven't shown you. It's new because it has a very important application, which I haven't shown you yet. But it has to do with that funny lazy 8 at the bottom, which has never really been considered to be a number in the way that I'm about to show you. So what I'm about to show you begins with simply rewriting 3 of these numbers so it's consistent with 1 over 2 in notation. Because It's a proportional quantity. And the numbers less than 1 are proportional on 1 in the numerator. But the numbers greater than 1 are proportional to 1 in the denominator, which is not only a mathematical relationship, but I'm going to show you that that establishes a geometric relationship between two reciprocal numbers that closes the family of curvature on a formula, which unlocks physics. Now, just bear with me, because I have to describe what I'm going to do before I do it, or you won't know what it is that I'm doing, and you might not listen. It is quite an art to broaching a new theorem, a new numbers system. It's not that I love to say that. I actually kind of get the willies whenever I say it, because I can't really believe what I'm saying. You see what I mean? It's like you hear yourself say this. I discovered. Believe me. I'm not loony at all. I swear, I've been doing this for 4 years, and I just get daffier and daffier. As indeed, it's like a split personality, because when I'm really cogent, I'm more cogent and erudite, eloquent than I've ever been in my life. Normally, I'm just a cut up and I like jokes. But in this case, I'm dead fucking serious, Daddy-O. I discovered a new number system, believe me, and now I'm going to show you. So remember, there's only 4 lines in this system. 2 of them are in families, and 2 of them are just there to make boundaries. And one of them is infinity over 1, and the other one is 1 over 1. Okay, I think it's pretty simple. But then the hyperbola, of course, is 2 over 1, and it just so happens that the way this is drawn, where a random hyperbola was selected and 2 just seemed like a good one, but it could be any one of the hyperbole that's in between the parabola and the straight line, which is a big wide range. Is it infinite? Yes, it is infinite, because it goes to infinity. So that's pretty much the definition. Infinity is in the system. Yes, it is. All right, so we have infinity over 1 for the straight line. We have 2 over 1 for this particular well-chosen hyperbola. We have 1 over 1 for the parabola. And then we have 1 over 2 for the very carefully chosen ellipse. How far does that go going down through the fractions? Well, if you keep going, you're going to get 1 over infinity. Are you or aren't you? That's the question. I'm asking you that question. It's hard to tell, but I'll prove to you that yes, that's where it ends. That's the inner boundary, is 1 over infinity. For the same reason that the other boundary is infinity over 1. Because you can see that all the numbers in between 1 and infinity have a reciprocal on the other side of the parabola. Does that make sense? I pray to God that it makes sense. I've been trying to say this in so many ways, in so many presentation series. I've made over 1,500 videos trying to tell you this. And I just wonder at the fact that it's like nobody's picked up on, nobody wants to interview me. Oh my God, what did you say, Scott? Kurchai Mungo's like, holy shit, it looks like he has the answer and none of my other guests have ever really figured it out, but Scott has. No, nobody's ever picked up on the fact that I actually developed a new number system. Yeah. Well, what good is it? Well, it solves the quantum paradox at all levels. I should go on, because the quantum paradox doesn't have levels. It has aspects. but I've solved the entire system of paradoxes of the quantum mechanical system. Which, if you don't by now realize that I'm probably out of my mind, I think you're strongly like, I'm not sure I need to listen to this baloney anymore. But that's why it takes so long. Because who could believe that kind of shit? Oh, I have the answer to the collapse of the wave function. Well, Paul Dirac didn't figure it out, but you did? I don't know what to say there. But then it goes further. Oh, much further. This describes the actual structure of the universe. At all scales. With a new numbers system. And that's... So I want to keep this under an hour, so I have 6 minutes to summarize everything for your dancing and dining pleasure. I hope I haven't worn you out. I know that a proof sequence can really be tedious. He's not getting to the point. But then once I get to the point, it's like, what? So you can't win. It's like walking a tightrope. I love it. I swear to God I'm the happiest man in the world. But that's very close to insanity. Meanwhile, I'm being interrupted by trains and sprinkler systems. But I'll tell you what, I'm not really interrupted by people. I've lived alone for 16 years since my wife died. I think you can see that living alone is probably good for me. It's absolutely necessary at this point. But now here comes the paradox. How come nobody wants to talk to me? I can't imagine why nobody would want to talk to me. So let me end with an anecdote, because I'm going to give another video later today, and I'm going to keep doing this until the solstice, which is only, I think, 5 days away. The summer solstice, and you know what the summer solstice is. I love to tell stories. I love astronomy. I love to talk about the stars, the galaxies, the quasars, the supermassive black holes, because I know it all. Yes, this is one reason I make these videos, is for self-therapy. Because I listen to all my videos and I'm just a gag and a gawk and a gape. It's like, I can't get away with sounding like that. So then, I straighten up. This is just a cycle, like a sine wave. And all of a sudden I'm talking with a British accent and just everything makes sense and nothing's deviant. And then 2 videos later, like, I discovered the secret of the goddamned atom, and why aren't you talking to me? It's like, zoo. Well, that's called elliptical behavior. I cover the whole range, Daddy-O. The age of 71, I have a right. But I'll tell you what, it's very good for me that I listen to these videos. I swear, I'm not exaggerating. I learn from my own videos. And I think that's enough. Because I don't want to wear myself out. I need to, get some fluids, get some rest. It's not even dawn. It's pitch black outside. Let's check the time. It's 5 a.m. I've been up for 3 hours. Scientists, of which I'm an apprentice, okay? I'm not trying to I'm Dr. Professor Sir Miller. No, I don't have any titles. I don't have any entitlement to anything. Except the freedom of a good American trying to do his best, Daddy-O. I'm going to... Okay, I can tell this is degenerating. I tried my best to get you to see that these are planar numbers, okay? And a plane... all these numbers have to be 2-component numbers. They have to be fractions. It's just that the fractions over 1... are fractions over 1. So all the fractions over 1 are fractions over 1. All the fractions under 1 are fractions under 1. God, I think I could have said that better if I tried. Well, there's a little poetry for you to wrap this up for your joy, your jollies. I hope you're at least a fraction as happy as I am, because I think I'm infinitely happy, all right? And that's enough. Thank you for tuning in. It really means a lot to me to know that somebody's listening. And I always am trying for this to be fun. But of course it's dead serious. There's no jolly involved here at all. It's for the future of humanity. And I'm leading the way, baby. I I don't use that word, by the way. It's a Hollywood term. Don't ever, you hear in these songs, you call a woman baby. Hey, baby. Do not trust that man at all. I told you my wife died 16 years ago. I'm beyond those kind of problems. As for having any kind of identity, you know what I mean? Everyone has an identity. Mine is very, very reserved. So I don't. Although I am tempted, the waitresses, the clerks and tellers who are female. Some of them are real good looking. Hey, I still have eyeballs. Okay. I'm tempted to do what my brother does, who's actually 14 years younger than I am. But he says to me, I'm of the age now. I call him darling. I'm like, well, you have some huevos. He goes, you don't. Oh no, they like it. They know that I'm not a threat. He does actually counsel women, or he has as part of his work. So my brother is something else, and he can get away with saying "dialin," but I don't think he would ever say "baby." Next time I talk with him, I'm going to ask him, would you ever dare say to a lady, "baby"? And that's an hour. Thank you so much. Don't miss the new moon. We're going to have a crescent moon either this evening or next, because the new moon was just 2 days ago. But that covers a span of about 3 days, where the moon, people stay up at sunset to see this, to be the first, and that's it. We'll be right back.